Hello, and welcome to week 5 of your online learning. Today we're going to start this last unit that we would be doing in class, and that's going to be on equilibrium and acids and bases. So we're going to start off with equilibrium. It says equilibrium occurs when the rate of the forward reaction equals the rate of the reverse reaction. Now this is super important to understand that when we talk about equilibrium, we talk about rates being equal, not necessarily the amounts. The amounts don't have to be the same. It just means whatever's going forward is the same thing as it's going backwards. So it says once equilibrium is reached, the rate of reactants being produced is equal to the rate of the product being produced. So if we have a reaction, A plus B, and now with equilibrium, we're going to see a double-sided arrow. When I draw them, it's usually like that, just to save time. And then C and D are the products. So what this would look like in a little graph here, now you're always going to start down here for your products, because usually you don't start with products, and you're going to start up here with your reactants. And I don't know how to change these colors, so I'm not even going to bother. I'm just going to put R for reactants, P for products. And so what happens over time as a reaction goes on, the reactants decrease while the amount of products increase. And when you have an equilibrium, at one point, they're going to start to level off. The point on the graph where they level off is where equilibrium occurs. Okay, so here you can see at the end I have more products than reactants. It can be the other way. You don't necessarily have to have more products than reactants. You could have a graph that looks like this. So it doesn't have to happen like that, but that's just, if you're doing a reaction, you want more products. So hopefully it looks like that one on the left. Now, equilibrium position is the concentration and gas pressure established at equilibrium. And again, we don't have to have the same amounts. We could have a graph that ended up to having, we'll pretend like those lines are the same, to have the same amounts, but it does not have to be the same. It just means however much product is produced, reactant is produced. And that's why those lines stay parallel, because what's happening in the forward and the reverse are the same. So equilibrium constant expressions, which is a KEQ, is the ratio of products to reactants at equilibrium. The higher the number, the more the products are made. The smaller the number, the more reactants remain. So if K is greater than 1, it favors the products. If K is less than 1, it favors the reactants. And usually we would want more products. So we want Ks that are greater than 1. To write an equilibrium expression, pretty simple. It's just going to be the concentration of products raised to their coefficients over the concentration of reactants raised to their coefficients. So in kinetics, we did rate orders, which we had to determine those exponents. Here, the exponents are just the coefficients. So if I was using this as the lowercase being the coefficients and the uppercase being the products and the reactants, my KEQ would look like this. It would look, so concentration of C raised to the C, concentration of D raised to the D, over concentration of A to the A times concentration of B raised to the B. Just so you know, brackets means concentration. We did talk about that already, I think, with solutions. So that would be the general form. Concentration of products raised to their coefficients divided by the concentration of reactants raised to their coefficients. Now, when we do this in reality in equations, only aqueous solutions and gases are included. We do not include pure solids or liquids. And so this chunk here is just saying K is greater than 1, the reaction favors the products. K is less than 1, the reaction favors the reactants. Because remember, you can go both forwards and backwards in this reaction, so we have to figure out what will we have more of? So we can write the equilibrium expressions for the following. We've got 2 moles of ammonia gas in equilibrium with a mole of nitrogen gas and 3 moles of hydrogen gas. These are all gases, so I can include these. So my KEQ is just going to be concentration of nitrogen. Oh, that looks like an H. N2, H2. I'm going to cube this, divide by concentration of ammonia squared. For the next one, you'll notice I have a solid here. I don't want to include that, so my KEQ would simply not have a denominator. It would be H2S times NH3. Okay. And then for the bottom one, the only thing we don't want to include is water. Water is a pure liquid. We don't want to include that. And so my KEQ for this, concentration of CH3COOH, which is acetic acid, square that. C2H5OH, which is ethanol, square that, divided by the concentration of CH3CO2C2H5, which is a compound that you do not know, just an organic molecule. Okay, so again, the whole point, concentration of products raised to their coefficients divided by concentration of the reactants raised to their coefficients. There should be a space here. This is unrelated. So we can take these and actually calculate a value for KEQ. So the first thing you want to do is always write out your expression. So we're going to do, all of those are gases, so they're all fine. H2O, CO divided by H2 and CO2. That equation is balanced the way that it's written. So all you want to do is just now plug in those values. So that's going to be 0.30. Well, that's for the CO. It doesn't really matter. 0.20 molar divided by 0.40 molar, 0.40 molar. And then put it in your calculator. The answer gives you 0.38 as my KEQ. And please note, there are no units for KEQ. For the equilibrium constant expression, there is no KEQ, no units. Which means if I was looking at this and this reaction was at equilibrium, I would have more reactants than products. So this next part says, what happens when an equilibrium has been disturbed by changing concentrations and a new equilibrium needs to be established? In order to do those calculations, you have to use a Rice table. So we're going to do an example on the next page, but I'm just going to show you what does Rice stand for. The R part is the reaction. So all you have to do is the balanced equation. The I is the initial concentration, which means you must have molarity, which we know is moles. Whoops, I ran out of space. Moles over liters. C is the change. So you either gain or lose based on the coefficients. And then E is the equilibrium concentration. Again, molarity. And to do that, you just combine I and C. So the I and the C lines come together to give you the equilibrium concentration, the E part. So let's look at an example and fill out our Rice table. So calculate the equilibrium concentrations for the decomposition of nitrogen monoxide. It gives us a KEQ value, which is a hint that you have to use a Rice table. We've got a 0.0150 mole sample of nitrogen monoxide placed into 12 liters. We have moles and liters that will be able to give us molarity. So let's go ahead and fill in our Rice table. So R is the reaction. It's the decomposition of nitrogen monoxide. Nitrogen monoxide will turn into the two individual gases of nitrogen and oxygen. Balance it with a 2 in front of the nitrogen monoxide. I is the initial concentration, so I'm going to take that 0.0150 moles and divide it by 12.0 liters, which I'm going to write here, 1.25 times 10 to the negative third molar. We don't have any of the product. We're just starting with nitrogen monoxide. The change. So I can't lose any of the product because I don't have any. So I must lose the reactant and I'm going to gain product because that's the only possibility here. Now the number here, I'm going to lose 2 of those. I'm going to gain that and I'm going to gain that. Okay, so that's my ratio based from my balanced equation. And now for my E, I just combine the I and the C. So this would be 1.25 times 10 to the negative third molar minus 2x. This would just be x, and that would just be x. Now the E portion is when you're at equilibrium. So what I can do now, write out my KEQ expression. Don't forget to square it. And now I just plug in my stuff. So N2 and O2, nitrogen and oxygen, are both x, so I'm just going to put x squared. On the bottom is going to be 1.25 times 10 to the negative third. Now this 2x, I'm going to, what's the word I want to use? Neglect it. I don't care about this minus 2x. Why? Because my KEQ value is so small. Since it's so small, only a very small amount of the nitrogen and oxygen will be made. And so since it's so small, I can neglect it, and it doesn't really change the amount of the nitrogen monoxide. If you don't believe me, just watch this. So I got all that in there. I'm going to plug in my KEQ now, 2.5 times 10 to the negative fifth. Multiply both sides by 1.25 times 10 to the negative third, and then take the square root. Okay, you know how to do algebra. When you do that, x is going to give you 6.25 times 10 to the negative sixth molar. That x is the concentration of nitrogen at equilibrium. It is the concentration of oxygen at equilibrium. Now what I need to do is I need to figure out what is my concentration of nitrogen monoxide. Notice that number is very, very small. I can now plug this number into this minus 2x, which we neglected in order to solve the KEQ. And I just plug that in there, and then I can say the concentration of NO is going to be 1.24 times 10 to the negative third molar. It was 1.25 times 10 to the negative third, so it barely changed at all, which was the whole point, which was why I could neglect that 2x. Another key thing here is you'll never have to do a quadratic. So if you come across a question and it asks you to do a quadratic to solve for ax squared plus bx plus c, you've done something wrong. You don't need to do that. Okay. Let's do another one. Let's see. When hydrogen iodide is placed in a closed container, it will decompose into its elements and an equilibrium will be established. If the initial concentration of HI is that and the Kc is that, what is the change in concentration? Okay, first off, a little bit different. It's giving me a Kc. Kc, the C is for concentration, which just specifically tells you that you're a solution. Whereas KEQ is just a general term. You can also have a KP, which you probably could guess would be for pressure. Okay. So we can go back here and set up our Rice table. The reaction of hydrogen iodide decomposing, HI decomposing into hydrogen and iodine. That's a 2. That just needs to be a 2 there. My I, it says 0.025 molar. That would be 0. That would be 0. The C, the change, that's again minus 2x. That's plus x, and that's plus x, again from our coefficients. And so E is going to be 0.025 minus 2x, x, and x. I'm not going to write out my equilibrium expression for you. I'm just going to plug it in. I know what the KQ or the KC in this equation is, 2.2 times 10 to the negative third. That's going to be equal to concentration of the products, so raised to their coefficients. So they're both x, so that's going to be x squared divided by 0.025 squared, again, because it is a 2 here. And again, I neglected the 2x. So I do that, and x is going to equal, it will be the concentration of the hydrogen, which will be the concentration of the iodide, which is 1.2 times 10 to the negative third molar. I can plug in this value here and solve for the concentration of HI at equilibrium, which will be 2.3 times 10 to the negative second molar. Okay. I just need to look and see if I did something up here. Oh, I didn't. I forgot to square this up here. That needs to be squared. Again, I squared it here. I forgot to square it there. Just pay attention to that. Sorry. I do make mistakes sometimes, very rarely. Oh, this is important. If you have concentrations of both reactants and products to start, so like in both equations we've done so far, we only had reactants and no products. Sometimes you could have products, no reactants. Sometimes you have both. So if you have both, how do you know if I'm gaining or losing products or gaining or losing reactants? So what you need to do is set up a Q. Q is K when you're not at equilibrium. Okay, so if you're doing a question and it's initial, so Q would be initial concentrations. K is for equilibrium concentrations. So if you're doing a problem, you have you have reactants, you have products, you don't know which way is it shifting, is it making products, is it making reactants? What you need to do is you have to solve for Q. Q is solved the same way as K, concentration of products raised to their coefficients divided by concentration of reactants raised to their coefficients. And so once you do that, I'm going to erase this so I can show you what that means. So Q, concentration of products to their coefficients divided by the concentration of reactants to their coefficients not at equilibrium. And then what you do is you compare your Q to K. If K is greater than Q, the reactants are favored, so you lose products. If K is less than Q, the products are favored, so you lose reactants. And if K is Q, you are at equilibrium. Okay. So keep that in mind if you come across a problem where you have both reactants and products initially. And then the last thing for these, for this part of the notes is going to be Lacheys Principle. Lacheys Principle states that when a system is at equilibrium and you disturb it for some reason, the system will respond trying to reestablish the equilibrium. Disturbances include changes in concentration, temperature, and pressure. So you're basically trying to undo what happened, okay? So when we talk about Lacheys Principle, we talk about shifts. A shift to the right produces products and uses reactants. A shift to the left produces reactants and uses up products. So let's see how the shifts will occur. For this equation here, you've got the iron ion, cyanide. I don't know what that ion is, whatever. In equilibrium with this compound here. So what occurs if I increase the concentration of this ion? So I have this just hanging out. I add more of that reactant. What you want to do is you want to use up that extra. In order to use it up, I shift to the right. What's going to happen? I make more product, which is why it shifts to the right, by using the extra reactant. So you use that extra reactant up, it shifts to the right to make more product. So now if I want to decrease the concentration of this iron compound here, if I want to decrease it, what I need to do is I need to shift to the left. Shift to the left will use up. Oh wait, no, I read that wrong. Sorry. If you want to decrease the if you decrease the concentration of that product, I want to make up for it and make more. Sorry, I confused myself there for a second. And I'm not good with editing, so you're seeing all of the mistakes. So what occurs if I decrease the concentration? I want to shift to the right to make up for what lost. Okay. Not the best time today. Okay, and then the last one, 2 moles of nitrogen dioxide is in equilibrium with dinitrogen tetroxide and 57.2 kilojoules. So I'm adding kilojoules here. So what happens if I increase the temperature? So if I increase the temperature, what happens is I now have more product, okay? So this temperature, so energy, whatever, if I increase the temperature, I'm going to have more of the product. I want to shift to the left to use up the extra energy. So what occurs when I increase the pressure? So increasing the pressure affects the side with more moles of gas, okay? So I have more moles of gas as a reactant. So if I increase the pressure, I'm going to have more collisions. More collisions will happen on the reactant side, which means it's going to shift to the right. So we're going to have more reactant collisions So more products formed, which hopefully makes sense to you. And then finally, what occurs when I increase the volume? So increase the volume, you decrease the pressure. So that's Boyle's law. So in this case, it's going to shift to the left. So if I increase the pressure, it shifts to the right. So if I decrease the pressure, it will shift to the left. And that's it for general equilibrium. We're going to talk very briefly about solubility equilibrium, but please make sure, and I know those Rice tables seems a little confusing. If you have questions about that, please ask, because Rice tables will come up again when we get into our acids and bases. Okay, so solubility equilibrium is a little bit different than the stuff we just talked about. Solubility, we know, has to do with dissolving substance in a given amount of water. We talked about that when we were talking about our solutions. However, even those substances that are deemed as insoluble, they do dissolve, if only an extremely small amount. So when we talked about our solubility rules, there were things that the rule said were insoluble. And I basically lied straight to your face because, one, you'd believe me, and two, it's fun. So what it means, if something is technically insoluble, it just dissolves so little that you don't see anything happening. So if a precipitate is present, the solution is saturated and an equilibrium occurs. So solute dissolves at the same rate as the solute precipitates. So when we talk about solubility equilibrium, you use KSP for the solubility equilibrium constant, and it shows how much substance will dissolve in water, which was found experimentally. So here we've got silver chloride being dissolved into its 2 ions, and it tells us the KSP is equal to the concentration of the products raised to their coefficients. When we talk about a solubility equilibrium, there will never be a denominator because you'll always have a solid as the reactant. Notice the magnitude of KSP. What does it tell you? It's times 10 to the negative 10th. That's extremely small, which is the reason why only very little of it dissolves. So let's see what we can do. So again, we're using those same things that we used for the general, but we're just plugging it into a different situation. So determine the KSP of lead chloride, lead 2 chloride, when the lead ion concentration is 1.62 times 10 to the negative second molar. So the first thing I want to do is write out my KSP. Well, actually, even before that, I should probably write out my equation. PbCl2 as a solid is in equilibrium with Pb plus 2 plus 2Cl minus. Those are aqueous. And it's important to include our states of matter because, remember, solids don't count. And so my KSP is simply Pb plus 2 Cl minus 1 squared. Now, the lead ion concentration was found to be 1.6 times 10 to the negative second. So but now, if I look at my balance equation, for every one of the lead, I get 2 chloride ions. So it's going to be 2 times 1.62 times 10 to the negative second, and I still must square it. So if I was to do this as a general thing, my KSP looks like this. Okay, so again, we must look at our balanced equation, and then we have to look at our equilibrium expression. So the answer to this problem, 1.70 times 10 to the negative fifth. And again, remember, equilibrium expressions do not have units. Okay, now we're going to try this one, determine the solubility of calcium carbonate. So first thing we should do is write out the equation.
is aqueous. Okay, balanced equation, which means my KSP will be equal to the calcium ion times the carbonate ion. Since it's a 1-to-1, it should be the same thing. So if I was to do this, this would be X, and that would be X, which would be X squared. So my KSP, which is 3.8 times 10 to the negative 9th, is going to be equal to X squared. All I have to do is take the square root of both sides, and then X will be equal to the concentration of the calcium ion, the concentration of the carbonate ion, which gives me 6.2 times 10 to the negative 5th. Now, X is a concentration, so you have to have units there of molar. And so that's just a little bit different for your solubility equilibrium. And I feel like that was really long, and some of those things may have been a bit confusing, and I seem to have been all over the place today, but please let me know if you have any questions. Read the homework assignments, work on those, send them to me. And again, please let me know if you have any questions. All right, so that's it. So I'll see you later.